Everyone, welcome back. So this is part 8 of 2026 being consistent, and this is the second video of our machine learning course. In this video, we will try to cover all the basic mathematics behind that and ensure that you will understand the process well, because it will comes in handy while you deep dive into the various machine learning algorithms, understanding how they works in real time, how data flows through them, how different operations are applied, and how, like if you apply an algorithm, how data is processed, and how does it produces an output, which like in the end gives you an result. So this is going to be one of the fundamental sessions of this machine learning course. And if the topics will not be covered in this video, we'll try to cover that in the second part as well. So let's start with that. Okay, so this is where we have left our like the first session on the introduction. Now we are going with the mathematical foundations, as in like this is the foundational step in the whole machine learning course, because if you are clear with the fundamentals and if you're clear with the like what's happening inside an algorithm when you choose to train a model, you will be more effectively choosing an algorithm, and you will know what kind of error it may cause on the data sets and how you're going to resolve them, how you're going to fix those errors, and how you can effectively make your model learn from its output as well. So these are some basic fundamental steps that defines the whole of the segment moving forward in the machine learning. So take study with the focus here, and let's start with it. So okay, our first is matrix and matrix operations. These are just simple. There are several things that you should be aware of while doing that. Starting with some are starting with like let's say what are the matrices, and why do we use them. So you have studied about like dimensions of the data. So 1D data can be represented as an array or anything like that. The 2D data matrix, which we all have studied in our young classes. And then the later, the advanced topic that comes are vectors, that are the combination of metrics that are basically three-dimensional data, four-dimensional data. And as soon as data advances and goes on and on, so like when we're training a model, we have to deal with like all kind of data and its dependency on various aspects as well. So that's where the various operations of the matrix and vectors comes handy as well. So going through the various operations of matrix, addition is basically simple. You just add the corresponding elements and get the result. Subtraction is also similar. It follows the basic mathematical laws like commutative, associative, identity, and inverse as well. Inverse is just basically inverse of 3 is minus 3. Identity 3 plus 0 is equals to 3. Associative is 3 plus 2 plus 5 is equals to 3 plus 2 plus 5 in the brackets. You can do that. Commutative is 3 plus 3 equals to 2 plus 3. These are some basic principles. Subtraction is also like corresponding, like the corresponding this minus this. Um, Subtraction doesn't follow the commutative law, associative law, identity law follows, and inverse also. Scalar multiplication is just basically like treat of this as a singular kind of data, and then when you multiply it by the scalar, all of the elements gets multiplied by it. And then we have the multiplication of the matrix. So there's a simple formula for that. So the formula for this is goes like rows with like columns of the first. So if you have the one matrix A, B, C, D and the other is I, J, K, so that's simple. A into I, B into K. First row, first column. So that's how you map the elements of the matrix from A to B to C, which is the product of A and B. Is not commutative. Obviously, like you're multiplying the row by column. So if you interchange the rows and the column, the whole logic is reversed. Is associative? Yes, we can do that. We can say that. Distributed? Yes. And cancellation law is technically not applicable. We will understand that later on. Transpose is very simple, like you interchange the rows and column basically. Inverse operation is just simple. You have to calculate the adjoint, and based on that adjoint, like you have to then calculate the inverse. So adjoint is nothing that basically that column. Okay, so if you have to understand that easily, like for a 2 by 2 matrix is just AD minus BC, simple adjoint. Here you can see. For a 3 by 3 column, you have to do that in a very simple manner. Like you have to take three elements first, and then you have to cross multiply, like ignore this row and this column, and then cross multiply the other two elements. So you can take any three elements. They should be of the same row or column. So you have taken this. So at and here it goes 0 into it. This minus this. So you have to just convert it into 2 by 2 matrix. So minus 2, 2 into minus 2 minus 4, something like that. Plus minus plus. So this one be minus 1 bracket, ignoring this 1 by 8 minus 2 by 4. So 8 minus 8 0. So this is reduced to 0. And then for that 1 minus 0 plus 3. So minus 4 plus 3, that should come out to be minus 1, I guess. Yes. And that's how you calculate that joint. And sorry, inverse, basically determinant of a matrix. And then you have to calculate the what we can say adjoint is just basically the values for all those. Like the adjoint at 2 is this, at 1 it will be what we have done. So you have to do that. So first calculate values for each and then transpose. And these are some simple mathematics. You can like try and practice based on them as well. So if you take a simple 3 by 3 matrix, and like let's do an example of that. Okay, 3 by 3 matrix example to just understand how we are going to calculate the joint. Let's take some decent example that should not be too hard. Yes, that can be hard. Okay, but yeah. So how are you going to do that? Um, let's just open the notepad. So the so the first element is 8. The adjoint of that will be ignoring this row, this column. So 6 into minus 8 minus 2 into 9. So that can be minus 48 minus minus plus 9, 18 minus 48 plus 18. That reduces to 30. 8, 30 minus 240. Minus 240 for that. For this ignored, minus minus plus 840 minus minus plus 1454 minus 4 into 54, so that comes out to be 216 minus 216. So similarly I just calculate for 3 and then we can do them. Minus 45, 6, 7, 42, minus minus plus, so minus 97 into 3, 9, 3 to 9, 291, minus 291. And suppose you have the values here as x1, x2, x3, y1, y2, y3. So the final adjoint would be minus 240, minus 216, minus 291, and from here you can have x1, y1, Similarly, here you have x2 and so on. So the main is to understand the idea, which is clear as of now, determinant and so on. And then you have some basic operations like inverse and all, and then you can understand the basic formulas as well, how transpose works, how adjoint works with different powers, and like how you can use inverse and so on. So just try to understand the concepts as we go on. These all will come in handy as we go ahead. Scalar vectors. You can go here, you can read the article and okay, yeah, scalar vector tensor. Vector is just basically fields that have directions as well. And tensor rank 2, like those three directions. Scalar 1 vectors just like you can say single dimensional array and tensor. We have multi-dimensional array as well. So vectors which have a direction, how the direction flows, the vector product, the unit vector is something definition you have learned in your class 11th or 12th, which is just a single magnitude of something in that particular direction. So the unit vector in I direction will be 1i, 0j, 0k, and others are 0. So that's how you treat that. Vector operations are very simple. This cross this will be go in that direction, 90-degree. Addition. So this and this will be vector addition of that. Just basically, okay. Addition rule is very simple. Like if you have two lines, I guess. Oh, okay. So in order to understand vector addition, like let's suppose you have one direction here. So you suppose, let's say so, you have given the direction here as well. So the addition of these direction will be like to make them continuous first of all. So this and just shift the direction here as well a little bit. So this will not change the overall result and magnitude. So the final one would be from the third side to the second side here. So this will be the resultant. You can calculate that by some mathematical formulas and you can refer them as well. Vector addition. Divergence is basically like differentiating a vector. Gradient is like differentiating in the unit direction as well. Curl, this is something that you might have learned in your second semester. So curl will be, if you are doing in one direction, you have to take the differentiation in other two directions as well. Laplace algorithms. Like here, you just have to focus on, like, you understand all of those. What are these things and what do they do? Why we are learning them? Uh, how they come in handy while dealing with complex machine learning algorithms, and are they really that much useful? All these questions will be answered later on, but take them as the kind of homework. Like you have to research on them, how how you can learn about them, and try to solve just one or two questions, just enough to understand them, not just try to master everything at the beginning. Otherwise, there will be a lot of questions as well. So scalar and vector fields. System of coordinates is just like Cartesian system XYZ, radius system, radius theta, and z the magnitude. Spherical is something similar theta phi. Sorry, we got that phi. Forgot that almost. So just go through it. And single value decomposition. This is something that you have learned in your first semester, I guess. Just basically calculating the rank of the matrix power method. And why these are useful, I've prepared that on the notes as well. Issue with tensors. What are the issue with tensors? High dimensionality. Like these are of high dimensions. Like suppose you are dealing with a machine learning model that has to take in data from 8 or 9 like parameters. And when all those parameters come together, the model will be too complex to perform some operations. So that why we are required with some modification or some reduction in the kind of data that um, our operations become easy, our models compute less cost, and it will be easier to maintain and debug the model. So that's where the principle of like single value decomposition, like of all the bunch of data you are compressing it to the single values. It's using like different uh, factors, PCA and this something like where you draw the curve. Okay, some algorithm I might have forgotten the name, but yeah, we'll draw all that. So this is some math regarding that. What is a UVD? What are U? What are U? V? What is D? These things you will cover later on here as well. Just don't worry. Singular vectors are just basically, as I said, the magnitude is one in the direction. Singular vectors defined above the substance space by them for is the best fit k-dimensional. You just can ignore all of them from now on. We will cover them in detail. Let it be around R matrix, the singular vectors of A are orthogonal. That is not much. Okay, singular value decomposition. Uh, yeah, here we get. So how we are reducing the dimensions? A is basically like you said n by d, which is 3 by 4, or let's say 8 by 9. So how we are reducing it? 8 by 1, 1 by 1, 1 by 9. So if you multiply, follow the composition rule, if you multiply these two first, so what will be the result? This to be equal to this, yes, resultant will be n into r. Okay, and then if you multiply this by this, r will be equal again, and then n into d. You get the same matrix. So that's how you are going to reduce the data by transposing by matrix multiplications as well. And in that also we have different kind of algorithms like we are transposing and first case singular vectors. Yeah, for any matrix P of rank at most k. These are just like theorems. You can read them; they're nice, but yeah, they're not much required. Power method also, like if you want to have the single value decomposition, uh, you can take that into consideration as well. Uh, Similarly, like okay, if you have an element and it goes like power k, and you want to compute it by that level, so either you multiply that by that much of time, or you follow that formula, which is what you can go above and like here you can find that out. A sorry, sigma, if I'm right, yes. And the volume of the cylinder, everything is given. Okay, yeah. Here we come with an example. The volume of the cylinder of height in an upper bound of the volume below 1 by 20 d. Proposition of the square we are calculating 2 pi vd minus 1 vd, and then we are applying the formula based on all those dimensions. So some of these things you can ignore, like it's too much to read if you're going for research base or something. It's fine, but for just doing for like moving advanced to ML and AI, you should have the knowledge of what these components are, what they do, and why they exist technically. So when you come across a model with its algorithm, with its various principles, you don't find yourself getting blocked like, okay, I don't know what's inside that, how that works. So you should be aware of that. Clustering, a mixture of spherical Gaussians, spherical surfaces, Gaussian products, all of that you have gone through. Okay, best fit kernel space, all of that. So you can go through them. We will be covering them in a little, what we can say, in a little faster way. A square matrix, the matrix can be chosen as a equality orthogonal. Okay, the Wikipedia article was similar. So go to the example if you feel stuck. A singular decomposition of the matrix is given by U sigma V. And if you multiply that by that and with that, you get something like, okay, V dash, V inverse technically you are as an extension, the left and right regular vectors of single value comprise all units in the co-kernel and kernel respectively of M, which a rank negative theorem cannot be the same dimension if M is equals to M, which is technically true. Like if you have the same dimensions of M and N, they can't be equal because they're using a different kind of value to transpose, they're transposing the matrices and so on. So of course that theorem stands for every of the for every cases for eigenvalue decomposition as well. Okay, so you can go through UV different columns and what all the operations we can do based on those metrics, all of that. So pseudo inverse, solving homogeneous linear equations, range, null space, rank matrices, low rank matrix approximations, as well like image compression basically. So what happens in CNN is you get the image, it is a like very high dimensional data. Let me search CNN data dimension. Input data layer is and S53 and it's somewhat kind of 16 to 16 to 12, somewhere 32 32. So you have to reduce the dimensions that where single value decomposition comes in handy. So based on that decomposition, you get to train your model better on what kind of image it can be, what are the things we can do, and so on. And yes, orthogonal matrix, similarly, lot those things. Spectral algorithm, variation characterization as well, calculation SVD, one-sided Jacobian algorithms. So you have to calculate determinant of one side based on that dimension as well. So yes, so that's how we can read and like go through all of them. So next thing comes, we have determinants and inverse of matrix that you've already covered. Eigenvalues, diagonalizations. Eigenvalues and eigenvectors are one of the most simplest topics. Like you have the matrix for eigenvalues, you have to like minus lambda identity matrix equals to 0, and then you have to calculate the different values of lambda by multiplying. So you get one or two values like determinant of that a minus lambda I equals to 0. So determinant of that is equals to 0. You get two or three equations, solve that, and then based on that, you have some eigenvalues, and by replacing those eigenvalues, you'll be having the eigenvectors. So it's that simple. Try one or two questions, and you will be good along as well for them. Now comes with calculus. So that's the topic where you have to give it some time, like what are derivatives, and if you don't already know, so derivatives, chain rule of derivation, gradient, Jacobian, Hessian. So these are all the topics that are in like normalizations, as I've said. We'll cover them later. We will be covering them in this video most probably. And discrete studies probabilities, yes. So derivatives. So what a derivative is? Suppose, okay, um, To understand that briefly, just like one of the most simplest way what I follow and what I advise is go to ChatGPT if you don't know about anything. What is to explain with an example and diagram if possible and explain it to me like I am 10-year-old. It's that simple. Um, no, of course, you don't want that. So just for the overview, like what is a derivative? It's just you have given a continuous function and then you have to find the value at a particular time. So how do you find that? Like you're given a very large segment and for the particular, use derivative, you differentiate, and then based on that, you calculate the values at that place. So limit and derivatives, this is the formula, like upper limit and lower limit, you have to apply minus h. And then after doing some of the operations, based on the function that is given to you, you will be left with some of the value. And from that value, you can calculate. Like h is just nothing, it's, you can say the smallest part, like tensor of change, that limit where h evaluates to 0, technically, h tends to 0. So if you take that change a plus close to 0 minus a upon 0, so 0 by 0 that comes out to infinity, but it's close to 0, not 0. So it's very small as compared to a. And suppose you have a simpler function like x squared. So how do you calculate the derivative? Um, you've given the upper limit, applying the square function, minus minus k square cancel, so 2h plus h square upon h, taking h common, 2a plus h, and h is very small as compared to a, it's tends to 0, so f dash of x square is 2a, which is a is nothing but x here, so it's 2x. Continuity differentiability is something like that. So suppose if a line is continuous on the graph, that we can say that the graph is continuous, and if a line is discontinuous, we can say it's discontinuous. Let me take you some example. So here we go. You get a simple equation like the equation for the line is this. But for discontinuous, you get two or three equations like till one, the equation of the line is this. At one, okay, till one, at one, it might be like you can give a static value like 3. And for greater than 1, the equation of the line is something you can say fx. So you have three equations for a line, and here we call it discontinuous function. So a function can be discontinuous and it can be derivative at the same time. And rule of computation, these are some simple derivative rules. Del of ex is ex, ax is ax log a, log x, derivative 1 by x, sin x is cos, cos is minus sin 10 x square x, and these are some simple formulas. Higher order derivatives is like you're differentiating them, you're differentiating the derivatives, and the chain goes on. Partial derivative is something, okay, like you have given an equation. Here you have two independent variables like an x and y. So you are differentiating first time based on x, and second time differentiating you are based on y. So that's how you do it. But okay, let's just start with the derivative. Let's see how it can give us something. Yeah, we can have images also. Example, velocity versus time. This is the classic example. Real life idea. Sometimes the road is flat, goes uphill, it goes downhill. Is the road steep here or flat here? Derivative tells us how steep the road is. Yeah, it is basically tell us the slope. And based on that slope, like how fast that is changing. So Suppose you have that, now pick a value. So the derivative of x square is 2x. What does one mean? It means that at x2 the value of y is increasing 4 units. Okay, so that's how you can calculate the change. So at that instant, how much value of that is changed? Like for x square, how much will be the y is changing? For like at x3, the value of y changes 23 by 6 units. So you can calculate that. And derivatives are used in like many places. One such as we are learning. So it's very simple. It will give very simple definitions. The action derivatives, total and Jacobians. These are all the other parts. Now we are coming to chain rule of derivation. Chain rule is just very simple. Like here you say, you just have to follow the simple mathematics. dz by dx, suppose the equation has y in it. So dz by dy and then differentiating the y by x. So at the end, dy by dy dot cancel and you get dz by dx. Like it comes in handy when you have the functional orders within the functions. So there you can differentiate it by first the inner, then outer, then outer, then outer. And then in the end, you are getting the final result as well. And sometimes it's not given like that. We assume the values, like some complex values are given, so we can let them y, then we differentiate based on y. And then from that y, we find that x and the chain can go as much the complex the equation goes on. If we have an example here, no, I don't think so. But yeah, don't need to go in detail, just understand, apply and practice one or two questions, and then we have the vector calculus. What does vector calculus do? Gradient basically is the slope. It tells us like how much steep or like how much is the path lagging at the current exact place. Hottest point in the oven, what is the gradient here? Zero, not a zilch. Why? Once you get the maximum location, there is no direction of greatest increase. A direction you follow will lead to decrease in the temperature. It's like being at the top of the mountain. A direction you move is a downhill. A zero gradient tells you to stay put. You're at the max of the function and can't do better. Next to it, now to get to the highest point, you have to go downhill first. Now yeah. Okay, so this is one of the classic problems in AI, the convex hull problem, we can say. We'll cover that later as we go on with machine learning algorithms and so on. But let me give you a brief idea. So, what happens is sometimes the model, what we're trying to achieve in the model is the maximum efficiency, but it has a certain point where it can have the local maxima as well, which is different from the global maxima. But as the model propagates in any of the direction, as you can see, here it's moving in a direction of the mountain, it will go downhill. The performance will degrade, and then it will like increase. So, in order to avoid that, what we do is we apply certain like algorithms, like until the global maximum is going, try all the approaches and so on. So these come in handy when we understand the later segments as well. So how gradient is calculated at each of the point while applying for the algorithm. So you have to go differentiating by each, like it has the three dimensions as you can say, x, y, and z. So you have to differentiate by each, and then you have based on that differentiation, you have to find the direction, and the direction, uh, what we can say is will lead to the increase. If you go in the direction towards that, it will help you to find the maximum minima calculation by vectors. That topic, if you read, it might comes in handy. Okay, maxima minima calculation by matrix. It's a very simple topic. If we get something written, I will be able to tell you. Okay, you are given a function. Step one, differentiate based on x, differentiate based on y. Set those values to 0. You will get some points, and based on those points, find those value, and then do a second order derivative. If second order derivative is positive, that local point might be the okay. That's for one variable. For two variables, you have to calculate the determinant as well. So which is second order derivative f. And how you are going to calculate like the values of x and y? The first order derivative, put that to 0. All the y's will get cancelled, I guess. And for fy, put everything 0 and x get cancelled. So you'll get some values of x and y. Take that as a point, and based on that point, calculate ffx, fyy, and fxy, which is same of fyx. So you can do in any matter. And that calculate d. If t is greater than 0, fx greater than 0, minimum, local maximum. D is less than 0, saddle point. Saddle point is basically, yeah, you are stuck here. You don't know where to go. So these comes like not very often, but yeah, sometimes inconclusive. So nothing is able to conclude from it. So that's how derivatives come handy to find the local minimum maximum points of a certain algorithm, a direction where it's moving, and the equations we are like making. So the equations will be from the models, and we have to like what we can say, we have to make it like as much optimized as much possible so that our model doesn't go in the wrong direction, and it will like strive towards the result better. Jacobian is something find collects the all first order partial derivatives, and that can be used for backpropagation, changing between the variables. So partial derivatives in machine learning as well. Okay, now we are coming closer to the inputs and like models. So error, what is error? By WK chain rule of, and one thing about chain rule is you can extend it as much as you want. Jacobian matrix as well, like based on differentiation of all the variants. Like if you have x fxyz, so fx1, fx2, fx3, you get the matrix kind of that, and then based on that matrix you do different kinds of calculation. So not given simple here. Jacobian, I'm putting that thing in the notes as well, just in case. What are these? Um, looks like the interest not on damages. Okay. So yeah, search those images as well if you want to find out about anything. And yeah, if you have marked down with they won't be that hard. So yeah, the solution as well. What is a Jacobian matrix? What does it do? You get you get v fxy v gxy. So Jacobian is u by x, u by y, v by x, v by y. What an example. You get two equations, find the Jacobian matrix. This is the Jacobian matrix. At a specific point, you get the specific point. You then calculate the determinant at 1 and 2, at negative, orientation flipped, preserved, transformation collapse, and everything within sites as well. So, it's a very simple topic to learn and understand, not much difficult as well. Hessian matrices are something like discriminants. Okay, definition of function Hessian matrix and its corresponding discriminants. The notice one second order partial derivative function of one of n variables. So suppose if you are having n variables and then it's similar to Jacobian as well, but here it's calculating that by degrees. So what happens in Jacobians is it will switch the variables here. It won't switch the variables, it's just switching the degrees to which it has to like find that stuff as well. So based on that x1, x1 square, then x1, x2, x1, x3, so on till the very end and then calculate all those determinants and so on. So it comes in handy, I guess, for the matrices where we have a like higher dimensions of data. Greater than 0, yeah. Local maximum x is less than 0. So yeah, it's simple. It's just similar to Jacobians, the working and so on. The formula is a bit different and it might be more optimized when we talk about the. So yeah, based on these Jacobians and Hessian methods, we get something like bigger dimension matrix and so on for different models, and then we can reduce them as per our needs. So this is something all about the part one. I have to end it here. So mathematics is fun if you just like try to do that on a regular basis. Not that much regular, but yeah. These are some topics that comes in handy while dealing with large sets of data, how to operate, how to handle them, what to like differentiation at each location means, how Jacobians are handled and so on. So you can understand about them and later more, like do your own research. You might come to know a few more things that I can not even explain in the video. And if you want the detailed explanation of any of the topics, please mention in the comments as well. So the main agenda of this is like all these topics you should have like ample knowledge. So if you are seeing anything, any algorithm, using them in any of the way, you have that idea. Okay, yeah, that works in this manner, and that's how it is using it, and it can result in this outcomes. And yeah, so then you can decide whether you have to prefer that algorithm or not. So that's the starting of it. Everything from the notes is something clear. Mm, okay, now let's save the markdown file. Let's leave it as this. Required. Let me just get it off. Issues. Non-uniqueness is something which you have discussed. Data pre-processing also. And yeah, this is something example that I brought up, like behavior can be categorized by k-dimensional vector, where k is much smaller than n and d. So how behavior can be extracted like n by k into k by d. So based on that k, we are grouping them together and doing many of the operations that helps us to in the reduction of the data. Otherwise, rest of the things are used for like searching online on ChatGPT and other stuff you can do as well. And like yeah, you can try them, do some homework, and till then we'll move to the next video. And as a reminder, part 10, yeah, I've got some freelancing as well to do side by side, and I'm also doing it. So It's going to be pretty hectic for the two, but it's fun as of now. Uh, so for any of the doubts, please mention in the comments as well. If you want any topic to be covered in detail, and uh, till then, like, share, and subscribe, and we'll cover the remaining topics in the part two of the mathematical sections for machine learning. Till then, take care. Bye bye. Good night. And happy Holi and happy Diwali from the Middle East, I guess, based on the current scenarios.